Hello students, I welcome you in today's session of physics, and in physics I am going to present you chapter number 23, which is your photoelectric effect. You can see here this is the chapter photoelectric effect, and it's a unit of dual nature of radiation and matters. Clear? So before going to start the chapter, let's have a discuss what we have to study in this chapter. First we discuss about the syllabus. So in syllabus you can see here photoelectric effect, Hertz and Lenard observations, Einstein photoelectric equation. So first we start with the photoelectric effect. You can see here this is the photoelectric effect. So what is the photoelectric effect? You can see with the figure. I will tell you what's going on here. So in 1887, Hertz observed that when an ultraviolet ray are made to fall on the negative plates of an electric discharge tube, the electric discharge become easier. Fine. So after 1 year, Helmholtz confirmed it experimentally. He explained two zinc plates in a vacuum bulb. Two wires connected to these plates were joined to a battery and a galvanometer. You can see here, this is the galvanometer, this is the battery. Then what happened? Helmholtz observed that when the ultraviolet rays are made to fall on the negative plate, this is the ultraviolet rays which are falling over the negative plate, immediately a current flow in the circuit, and as soon as the ultraviolet rays are stopped, the current also stop. Fine. So if on the other hand, the ultraviolet rays are made to fall on the positive plate, then no current flows or a very feeble current flows. So Helmholtz, however, could not explain this phenomena. Now in 1898, J.J. Thomson established that when the light falls on a metal surface, then electrons are emitted from the surface. So in 1900, Lenard told that when ultraviolet rays fall on the negative plate, the electrons emitted from the plate are attracted by the positive plate. Clear? So that the circuit is completed and the current start flowing into the circuit. But if the ray falls on the positive plates, then electron emitted from the plates do not reach the negative plates because the electrons are negatively charged. Fine. So hence the circuit is not completed and the current does not flow. So you can see here, this is the definition of the photoelectric effect. You can say that the phenomena of emission of electron from the metal under the effect of light is called the photoelectric effect. Fine. This is the definition. Now the electrons emitted by the photoelectric effects are called the photoelectron. Those electrons which are emitted due to the process of photoelectric is called photoelectron, and the current produced is called the photoelectric current. Clear? For this phenomena, the light of short wavelength of higher frequency is more effective than the light of long wavelength or low frequency. Now come to here the topic 2, which is your Hertz and Lenard observation. This is also the important one. So Hertz and Lenard performed many experiments on photoelectric effect. They took plates of different metals and illuminated them with the light of different frequency and of different intensity and measure the energy of the photoelectrons and the strength of the photoelectric current in each cases. So they obtained many results related to the photoelectric effect on the basis of these experiments. So a simple experiment arrangement you can see here in the figure below. I will show you. So it consists of the two metallic plates P1 and P2, which are fixed at some distances apart from each other in an evacuated tube. Let us see the figure below. Here is the figure. The plate P1 is in front of the quartz window W. This is the you can see the light ray coming from this window. This is the window. Fine. Through which the light ray fall on it. So it is a cathode plate. The plate P1 and P2 are connected to the microammeter and to a potential divider through a commutator C. You can see here there is a key and a microammeter is attached here. So through this arrangement, the potential difference between the two plates, which is of P1 and P2, you can see from this figure, this is the plate P1 and this one is the P2, can be varied, and the direction of the potential difference can also be changed. This potential difference can be measured by a voltmeter. Clear? Now here you can see the whole complete figure. This is the figure of Hertz and Lenard. So what is the dependence upon the intensity of light? This one we will talk about. So when the light ray of definite intensity and a definite frequency fall on the plate P1, the photoelectrons are emitted from the P1. So if the plate P2 has a sufficient positive potential in commutator C, so plugs are inserted in the gaps. You can see from this figure, this is the commutator. Then what happened? then all these photoelectrons reach the plate and a maximum photoelectric current flow in the circuits. So on increasing the positive potential of the plate P2, there is no increase in the photoelectric current because all the electrons emitted from the plate P1 are already reaching the plate P2. Now if however we double the intensity of light falling on the plate, the maximum photoelectric current is double. Clear? This is the important one, and the reasoning type questions might be arises in your examination. Clear? So this means that the photoelectric current or the rate of emission of photoelectron is directly proportional to the intensity of incident light. Please keep in mind what's going on. Now you can see this is the graph. A graph between the photoelectric current and the intensity of the incident light will be a straight line. You can see here the straight lines are coming. What this showing on now, if by inserting the plugs in the gap 2 by 2, the commutator C, we give a plate P2 a negative potential which is relative to the P1. Then the current immediately decreases but does not become zero. So this shows that the electron emitted from the P1 have kinetic energy, and on increasing the negative potential of P2, the current falls rapidly. Clear? And finally becomes how much? Zero. So at this stage, even if we increase the intensity of the light falling on P1, the photoelectric current is not obtained. This shows that P1 emit electron of different energies. So when the plate P2 is at a small negative potential relative to P1, it repels these electrons. Therefore, the electron with a small kinetic energy do not reach the plate P2. Fine, which is of high energy, electrons still reach. Now P2 as the negative potential of P2 is increased, the number of electron reaching P2 goes on decreasing. So finally a certain negative current becomes zero. So you can see here, this is the important one, the negative potential of P2 relative to P1 at which the photoelectrons current becomes zero is called the stopping potential or cutoff potential. This is important one. So please keep in mind what is the stopping potential. This is the definition at which the current or you can say that the potential at which the photoelectric current becomes zero is called the stopping potential. Now since the stopping potential stops the maximum energy electrons, it is a measure of the maximum kinetic energy of the electrons. The stopping potential be V naught, then the maximum kinetic energy, which is your EK of the photoelectron, will be given by, this is the relation between the photoelectric current and the electron, that is your V naught, where V is the charge on the electron, and I hope you know very well what is the charge over electron, which is 1.6 into 10 to the power minus 19 coulomb. Now since that the stopping potential, the photoelectric current cannot be obtained, so by increasing the intensity of the incident light, it is clear that the stopping potential or the maximum kinetic energy of the photoelectrons does not depend upon the intensity of incident light. You can see here this is a graph between intensity and the photoelectric current. So you will get here a constant frequency. So if an accelerating potential of the anode and the frequency of the incident light is kept constant and the intensity of the incident light is vary, then the photoelectric current, that is the number of photoelectrons emitted per second, is proportional to the intensity. You can easily understand by seeing the figure number 4, this one. Fine. Now this is given here the dependency upon the frequency of light. So I'm not going into the very deep section. I just tell you, just see the graph below given here. These are the graphs. So what's the maximum kinetic energy of the photoelectron increases linearly as the frequency of the incident light increases. This is the effect of frequency of light. With the help of your figure, you can easily understand it. Now here it is written that if the straight lines graph between the EK and nu is extended backward, if the intensity of the frequency y-axis at point V0 and intercepts, so the energy axis, that is minus B, this means that for the photoelectrons to be emitted from a given metal plate, the frequency of the light incident on the plate should be higher. Fine. Then the nu naught. Nu naught is the frequency. So if the frequency is lower than nu naught, then no photoelectrons will be emitted, whatever be the intensity or the duration of light. So you can say that nu naught is the threshold frequency, means the maximum frequency at which the ejection of electrons on the metal surface is possible. You can see here, that is the thing written here, the lowest frequency of light which can emit photoelectrons from the material is called the threshold frequency, or you can say it's cutoff frequency of that material. So it can be read directly from the graph. The above graph can be represented by the equation EK is equals to A nu minus B with the help of this graph, where A is the slope of the graph. This equation is an experimental result. So if we perform experiment with plates P1 of two different matters, 1 and 2, so you can say here we find that the graph between the maximum kinetic energy EK and the frequency of light nu in each case is a straight line. Here you can see here. So these straight lines are parallel to each other, and the slope A is same, whereas the value of u naught and b are different. This means that the equation ek, this one, minus b, A is a universal constant and b depend upon the masses of the cathode plate, materials of the cathode plate, sorry. So it is evident from that graph that when v is nu is equals to nu naught, then ek is equals to how much? 0. Fine. So hence from the last equation you can write here b is equals to a nu naught. I hope you understand it. Now come to here, the minimum energy which is required, the emission of photoelectron from a metal surface is called the work function of that metal. This is the definition of work function. That is, the minimum energy which is required for the emission of electron from the metal surface is known as the work function. Clear? Now here you can see there are the few laws of the photoelectric emission given here. So just read the laws. What are the laws? So Leonard and Millikan give the following laws on the basis of experiment on the photoelectric effect. So first one, the rate of emission of photoelectrons from the metal surface varies directly as the intensity of the incident light falling on the surface. Now the second one, the maximum kinetic energy of the emitted photoelectron is independent of the intensity of the incident light. Now come to the third one, the maximum kinetic energy of the photoelectrons increases linearly with the increase in the frequency of the incident light. Now the fourth and the last one you can see here, if the frequency of the incident light is below a certain lowest value, then no photoelectrons emitted from the metal. So this lowest frequency or threshold frequency is different from the different metal. Fine. Now comes to there is a fifth one also. As soon as the light is incident on the surface of the metal, the photoelectrons are emitted instantly. That is, there is no time lag between the incidence of light and the emission of electrons. I hope you understand it. Now there is the contradiction why this theory is failed. You just read it by yourself, and if you still feel any doubt, you can ask me in the comment section. Now come to the Planck photon hypothesis. This is the most important one, which is the quantization of radiation. So you can see here, the black body radiation has in general all the wavelengths from 0 to infinity. So at a temperature, the total radiation energy is distributed among different wavelengths. So this distribution was experimentally studied by Lummer and Pringham. So no formula was based on mechanics and thermodynamics could be obtained which could express the distribution of radiant energy among the different wavelengths at a given temperature. This was a big challenge for the scientists. Now in 1900, Planck put forward a revolutionary idea that the emission of the radiation is not a continuous but takes place in the form of small bundles or packets with a definite amount of energy, which we are called them quanta. Clear? So later on, these bundles, which are called photons, the energy associated with each photon quantum is how much? H nu. You can see here, where nu is the frequency of radiation and h is the Planck constant. So this emitted energy may be h nu, 2h nu, 3h nu, but not in between. Suppose the wavelength of some visible light radiation, that is 500,000 angstrom. So according to the c is equals to nu lambda, where c is the speed of light, the frequency of this radiation can be calculated. Fine. So according to the Planck hypothesis, the energy of each bundle or photon of this radiation comes out to be 4 into 10 to the power minus 19 joule. So hence, according to the Planck hypothesis, the exchange of energy by radiation of wavelength 5000 angstrom is possible only in integral multiple of 4 multiplied by 10 to the power 19 joule. So Planck, on the basis of his hypothesis, gave a formula for the energy distribution which was found in the complete agreement with Lummer and Pringham experiments. In 1905, Einstein explained photoelectric effect on the basis of Planck photon hypothesis. Clear? Now here's Einstein explanation of photoelectric effect. What Einstein gave his formula. And after that we have to there are certain more topics we have to cover out. So this is the fifth one. Clear? So what is the Einstein explanation of photoelectric effect? So in 1905, you can see here, this is the topic. In 1905, Einstein explained photoelectric effect on the basis of his Planck's quantum theory. Fine. Now according to this theory, light travels in the form of small bundles or packets of energy which we are called as photons. Now the energy of each photon is how much? H nu, where nu is the frequency and h is the Planck constant. So the intensity of the light depends upon the number of these photons. Fine. So when a photon falls on a metal, it transfers the whole of its energy h nu to any one of the electron present in the metal, and its own sign existence is vanishes. So a part of this energy is used in ejecting the electron from the metal, and the rest is given to the ejected electron as kinetic energy. So all the electrons which are ejected from the metals and the rest is given to ejected electron as kinetic energy. That is, all the electron which is ejected from the metals are not ejected from the surface only, but also from the interior of the metal. So the electrons which are ejected from the interior of the metal expend some of their acquired energy in collision with the atoms of their way to the surface. Fine. Thus, the electron with different energies are emitted from the metal. The electron emitted from the surface of the metal have maximum kinetic energy because their energy is not lost by collision. Now suppose the maximum kinetic energy of photoelectrons which are emitted from the metal surface is how much? Ek, and delta W is the work energy required to eject a photoelectron from the metal, and W is called the work function of the metal. Then according to the above explanation, we can write here the equation how much the Planck's constant, that is h nu, is equals to W plus Ek, or you can write it Ek equals to h nu minus W, where h nu is the energy of the photons which are absorbed by the electrons in the metal. Now these are the two equations you can see here, the first one and the second one. So comparing these equation with the experimental equation, Ek is equals to a nu minus b, and become clear as that A is actually Planck constant h and b is the work function W of the metal. So if the energy or the photon absorbed by the electron is less than the work function of the metal, then what happens? The electron will not be emitted. Therefore, if for the given metal the threshold frequency of the light be V nu naught, then the maximum amount of energy, so h nu naught of the photons of light, will be spent in ejecting the electrons out of the metal. That is, it will be equals to the work function, which is equals to h nu naught. Now substituting this value of W in the last equation, we get here Ek is equals to h nu minus nu naught, or you can write it Ek equals to h nu minus nu naught. Now here are the cases given. What is, if the maximum velocity of the emitted photoelectron be V max, then you can write here Ek equals to half V max square. Hence the equation may be written as half V max square is equals to h nu minus nu naught, or you can write it hc is equals to 1 by lambda minus 1 by lambda naught. So this equation is called the Einstein photoelectric equation, and this is the most important one, so please remember this. The laws of photoelectric effect can be explained by this equation. Clear? So and now I'm moving to the determination of the Planck constant. How you can determine the value of the Planck constant? So here you can see with the help of graph, Millikan plotted a graph between the stopping potential. I already told you what is the stopping potential, V naught, and the frequency nu of the incident light of the photosensitive surface over a wide range of frequency, and obtain a straight line, which is figure number 8. Now the Einstein photoelectric equation is, this equation we had already proved in the above expression. Now since the stopping potential just stop the maximum energy photoelectrons, we can write it half m V max square is equals to E V naught. Clear? So this is your equation 1, and this is comes out to be second. From the first and second, you can write this E V naught equals to h nu minus nu naught, or you can write this equation V naught is equals to h upon E nu minus h upon E nu naught. So this is the equation of the V naught versus nu graph. It represents a straight line since h and E are constants and nu naught is constant for a given surface. Now according to equation 3rd, this is your equation number 3rd, the slope of the straight line graph is h by E. So you can write it h by E is equals to how much? Tan theta, which is your BC by AC, or you can write it h is equals to BC by AC multiplied by E. Clear? So using the known value of the electromagnetic charge or electronic charge E, the value of the Planck constant can be obtained. Fine. Now this there is a relation between the energy and momentum of photon. I hope this is the last one, so just cover it. So the rest mass of the photon is 0, but its kinetic mass is not 0. The photon travel with the speed of light, which is c. According to the Einstein mass energy relation, you can know very well, E is equals to h nu, or in place of h nu you can write it mc square. So hence the kinetic mass of the photon you can write here m is equals to h nu by c square, but there is a relation of also frequency and wavelength, which is nu equals to c by lambda. So in place of nu you can write this value m is equals to h by c square c by lambda, or you can write it h upon c lambda. So the kinetic energy of the photon is m is equals to h nu by c square or h c by lambda. Clear? So the momentum of the photon, which is p is equals to mv, you know very well there is a relation between linear momentum p by p is equals to mv. Fine. So you can write h nu by c square multiplied by c, or h nu by c, and where nu is equals to c by lambda. So you, after putting the value, the momentum of the photons comes out to be like this. Clear? I hope you understand it what I taught you, students. So this is the end of the chapter, and we will meet with the next lecture with a new topic and the new chapter. Till that, students, do study. Thank you, class. Thank you very much.